The second goal was just bridge between the skill gaps that academic training provide at undergraduate level and automated synthetic approach, which is common in chemical industry. The goal was develop a low-cost, viable technology, less than $1,000, to democratize synthesis. Next, please. So we designed two activities. Rachel and Saad, mainly they took the lead in this. They designed two activities, and the activity number one is ideation. How do we introduce automation to the classroom? And activity number two was brainstorming / prototyping. So we try to just first activity. So the general idea, how we can introduce automation to undergrads and inspire them and prepare them for chemistry jobs and chemistry automation. So in brainstorming, we talked about what goes into the box. So each group worked with each other to come up with a prototype to represent the kit and develop a budget. So just reminding you, the budget, we try to keep it below $1,000. Next. So we start with activity number one, ideation. So we had three groups, and Marty, Rachel, Saad, myself, and Tim, we went to different rooms and we talked about them. I'm going to ask Marty to help me out in some of the rooms because I wasn't part of the conversation in all of them. So the first group, the question is, do we even need to introduce automation to undergraduate level? The challenge they presented is a rigid structure of the undergraduate curriculum. Literally, there is no time to include that. And the second follow-up question is, are we exposing them? Are we giving them an experiment, or are we teaching them how to automate? Is coding necessary? A little bit of coding is necessary. Do we need to teach them Python? So a faculty believe that chemists need to learn how to do things by hand and appreciate the difficulty of that. So, and highlighting the importance of the batch chemistry. And they believe the introductory courses, they need to be taught in the old school way. But if we decide to do that, so the design of experiment, something needs to be aqueous, easy synthesis, and the goal needs to be show the repetitive nature of the automation, and reproducibility is very important to teach to our students. That the type of operation we can just provide for upper level classes, they should be cheapest, easiest, and have a wow factor. The example they provided is automation with the Raspberry Pi, which is a cheap technology, inexpensive technology. Marty, you were in that room. Do you want to add something to this slide?
Sure. Thanks, Arsalan. I think a couple of the other really great ideas that emerged were to leverage the locally available resources. So then the box could become a entryway into utilization of, for example, other things that would be in the classroom. Everything from maybe there already is a balance to also some very creative ideas about how to use the iPhone or local kind of, cameras that might be able to be integrated as part of the readout. So I thought that was really creative. There was also a good discussion about there's an inertia to curriculum and that people have a fixed way of doing it. And sometimes it's very challenging to kind of disrupt the curriculum. So if you could find an activity that just kind of naturally integrated, like take a lab that's very common and that's usually done by hand and just make an automated variant, then it would be easier for professors and teachers to kind of work that in without having to rewrite the whole curriculum. And the last one, you kind of touched on this a little bit, but the data science question came up, was very interesting. If there's an AI or data science component, we've got to be really thoughtful and careful about making sure that the professor or the teacher feels comfortable with those same concepts, and perhaps even including a train the trainers aspect so that you can bring everybody on board to feel comfortable doing the exercise. So those were some of the ideas that came up.
Thank you, Marty. Next, please. So in one of the group of sessions that I was involved, me and Tim, so the question was the students' involvement. We had a group of the very young PhD students, and I asked them about their undergrad experience. In his opinion, it's very important how to communicate with the younger generation. So, and he believed that we need to start from the middle school and the high schools. So the design of experiment needs to be something interesting for high schoolers, like a function focused experiment that they can understand how they can use chemistry in their everyday life. We had a very interesting discussion with a high school teacher. So he mentioned the problem is most of the students are not very interested in chemistry because it's a difficult subject and they want to just get the AP chemistry and never come back to chemistry again. The solution he provided that we need to provide some projects and implement automation and robotic. He believes the robotic is a very interesting subject for a younger generation. And with implementing robotic with the real world application, we would be able to encourage them and inspire them to pursue chemistry as a future career. So the example he provided is like a vaccine, the vaccine, COVID-19 vaccine. Everybody knows about it. And if we can just use some sort of very easy projects related to vaccine, a lot of students would be very interested to learn more about it. So Marty started the session. He said he became a scientist because it was a wow moment for him when he made an aspirin in the chemistry lab. We all had the similar experience. So he believes we can provide that type of moments for our students to pursue them to come to the chemistry. Next. The second activity was brainstorming. So the question is what goes into that box, how we can design a box with less than $1,000 to democratize synthesis, to send it to all the schools with limited resources that everybody can teach it. Everybody from an adjunct to the PI would be comfortable teaching that. So a faculty just he recommended auto titration. It's easy way to build the automation. You can have 97 plates. It's a tedious job to do it with hand. It's easy to do it with a robot. So the orange juice from the FDA standard can be used as an asset to provide an industrial example. Obviously, the design needs to be easier, faster, and more reproducible. They don't need to worry about the pH because we can provide a pH probe, and some syringe pump can be used to design that type of experimentation. Another idea was just using the kinetic analysis if we want to implement robotic to Gen Chem, and it can help the students to go through the Gen Chem and also find interest in the PChem too. Marty, do you want to add something to this slide?
I think similar, the question came up around, do people have a GC or do they have an NMR or other types of equipment, and really trying to think about the different audiences where there may be zero in terms of availability of equipment to couple to it versus in an undergraduate, there might be a lot more resources available, and that would change what does or doesn't have to go into the box to complement the local surroundings. So there was a really good discussion about that.
Wonderful. Thank you, Marty. Next, please. So they came up with a budget. So if we use a Raspberry Pi, $100 is a computer, is cheap, need a monitor, obviously, the liquid control, and they came up with a really reasonable budget. So they can put a cheap camera, inexpensive camera on the Raspberry Pi. It requires a lot of coding to make that computer working and communicating with the instrument. And also some organic reactions they provided, so Greenyard and Suzuki, they are air sensitive reactions. It might be a little bit challenging to design that type of experiments for the organic chemistry 1 students. Sorry, Marty, can you just jump in? Do you have anything to add to this slide?
No, this was, again, I think the discussion around picking a reaction and trying to make one that would be able to be done in water, so avoid any type of organic solvent requirement. And then you mentioned the air sensitivity, but of course there are ways to do a Suzuki mirror coupling under air. And that one actually, I think was pretty interesting to think about as a modern reaction that could really open up people's eyes to what's possible in terms of snapping carbon-carbon bonds together. So yeah, there was a lot of enthusiasm for that.
Next, please. Thank you, Marty. So in our session, we started to talk about how we can design something interesting for the students. So we came up with a system for designing an ionic liquid or a salt with amino acids that it can take up CO2 from the air. So David, high school teacher, he said it has to be interesting. Like climate change, we decided to design a material to fight the climate change. So maybe the scheme is not chemistry-wise very accurate. I'm sorry, I didn't have that much time. So what we did is we decided to just go to Costco and buy a protein powder. It contains 3 amino acids. We can do the simple acid-base reaction. Is a very basic concept. I remember the first time I met Rob, we talked about how to teach organic chemistry to students. And Rob said the entire organic chemistry is a reaction between the nucleophile and electrophile, and acid and base. If we can teach that concept to our students, we would be able to have a better organic chemistry experience. So we decided to do that. It started with very simple equilibrium, very fundamental concept of that. Amino acids are non-toxic materials, they are cheap. We do the titration. Gen Chem students can do the titration. So these materials can take up CO2 from the air directly. And if you see the picture below, so the salt is liquid at room temperature, and when it takes up CO2, it becomes solid. So it's visible for the general chemistry students, and they can see how chemistry can help to fight the global warming. We also can just go to the organic one, and we can provide experience for students to use NMR, the carbon-13 NMR. They can run a carbon-13 NMR on the product, and they would be able to see the carbon peak, the CO2 carbon peak. So the whole experience is just providing a fun activity for the students. They would be able to see the CO2 capture. And also one of the learning objectives is to show students that chemistry can help to have a better world. Like Marty said, we have to use the water as a solvent to keep it safe and inexpensive. If we decide to design that box and send it to the high schools, it has to be safe, and everybody needs to feel comfortable working with that. I talked to the program officer for the IU's program for the undergraduate education, and they believe we need to design experiments for the general chemistry 1 and organic chemistry 1, because it's a larger group of students can have that exposure compared to the upper level classes, because less students come to the upper level classes. So I asked him, so can we just have this box for less than $1,000? And he believes we would be able to design this experiment for less than $1,000. We didn't have time to come up with a budget, but this is experimentation we propose. Next, please. Oh, I have. No, I want to just have more time for some questions. Please let me know how we did that. Feel free to email me, or you can DM me on Twitter. And Rachel came up with an idea. She believes let's have another workshop this winter, supported by UIUC. And if you are up to, please let us know, and we would be more than happy to plan that. Thank you very much, everybody. And if you have any question, I would be more than happy to answer that. Oh, we have some in chat. Could you send me some projects for requirements in addition to general chemistry classes? Yes, absolutely, Louis. So these are just all ideas. We implemented this project in my Gen Chem 1. We got good feedback with the students, but we need to work with the larger group of students to collect data.
Arsalan, we have a couple of hands raised.
Right. Go ahead. You take the lead, please.
Oh, I was gonna just let you.
Okay, please go ahead. Jake?
Yeah, thanks. Can you hear me?
Yes, I can hear you.
Okay. One of the things I wondered if you talked about is I've seen a few projects like this out there where the fact that you're collecting data electronically gives you the ability to do better statistics on how all of the reactions go collectively. So rather than having 20 students each do their own experiment in isolation, you're in a situation where you can pool the data and they can actually learn about reproducibility in that context and learn about averaging and things like that. And I wonder if you discussed that aspect of it, because potentially that's not even just limited to the school where you're doing it, but you could imagine, pooling data from all sorts of places and then doing, different kinds of analyses that way.
I know there was some discussion about the remote synthesis classes. I let Marty to take that question. I think he was in that room, if I'm not mistaken.
Yeah, so I couldn't agree more, Jake. It's such a cool opportunity, not only to get students locally working together and to think about the power of data science that they generate, but we love this idea of distributed network around. You can imagine schools having this very fun, like parallel exercise. They all share the data, they all process it. So we're actually, as part of the Molecule Maker Lab Institute at Illinois, we've got a whole network of kind of thought leaders in education from high school up to college. And actually that's one of the ideas people are most excited about. So we're trying to think about piloting something in the spring that would allow us to go after that type of an experience. And I agree with you. That's when we really get people fired up, and to see that and couple that to let's save the planet, right? So I love what Arsalan said. If you start this discussion with let's get rid of the CO2 in the atmosphere, okay, now you've captured my imagination, and now tell me I get to team up with people across the country and the world to do it. Okay, now we're talking. So yeah, I totally agree.
Thank you, Jake. Louise?
Yeah, Louise, I just asked you to send me some information for number one, recruitment, and also for curriculum development. So right now I'm working on the OER, Open Educational Resources. Right. So that's one. Why I'm asking you to help, or anybody from this team. Our school is a Hispanic serving institution.
Wonderful.
I developed my own lectures or automation, I think, based on my knowledge, but I believe we all have different perceptions on the automation, the lab automation. I'm more focusing on the characterization. So general chemistry, analytical chemistry, possibly organic. So that's what I'm working on. But I think some help from all of you would be greatly helpful. Thank you.
Absolutely, Louise. MML, so Marty's Research Center at University of Illinois Urbana-Champaign, they have fantastic plan to involve large group of PUIs. And I'll let him if he wants to explain more.
Yeah. I will email to you.
Yeah, you can email me. I'll just send it to Marty.
Can I just capture this slide?
But thank you. Alan, our first speaker, Alan, please.
Oh, thank you. This is great to be here. Sorry that I missed yesterday. I just want to add to what a lot of that has been said.
Please. To
say that these modules are so trans-usable that, for example, in the acceleration consortium that we're running in Toronto, we think you can use modules like this all the way from undergrads, but even for training people from industry that want to enter this field. So I just want to also raise the attention to that this is kind of like intergenerational, and a lot of people need to be retooled into the digital chemistry. And I don't know if that should be also part of a report or whatever it's going to come out of this workshop.
Thank you, Alan. Thank you. So Linda, I think we should move on to the next person. I took up a lot of time. I apologize.
Hey, you're right on.
Thank you, Marty. Thank you, everybody.
My pleasure. Thanks, everyone. Thanks for the feedback.
I think next we have breakout session 2 report out from Dr. Anne LaPointe.
Can everyone see my slides? Not in full screen mode, it's in presenter mode.
Oh, it reverses it. How about that?
Perfect.
Yes.
Cool. So at breakout session 2, Nikki, Pohl, and I were discussing developing an online open source textbook for modern automated and accelerated chemistry. And so the genesis for this breakout session was when the planning committee was thinking about what topics would be of interest. We realized that pretty much everyone working in this field learns it as they're doing it, either in graduate school or in their postgraduate positions. And, even though, people have been doing this for many, many years, there isn't one general textbook geared towards people that want to get a broad introduction to the subject, and definitely nothing geared towards teaching an undergraduate or graduate class. And so we started thinking about what a textbook would look like. And, as I said, the main motivation was just to, really help people who are wanting to learn the subject and people who are teaching the subject, and, just increase interest in the field. And we thought about the format, and pretty quickly on, we decided that, an online living document would be appealing, A, for overall accessibility to a wide range of people, not just students taking a class. B, it's much more affordable for everyone, and that will serve our goal to make this kind of chemistry accessible to everyone. And the other thing that's really exciting about doing an online open source textbook is that we can crowdsource from a wide range of people who have expertise in this field. And this is especially important because it's such an interdisciplinary area. It's not just one subfield of chemistry. It's encompasses all areas of modern chemistry, as well as computer science and engineering. So that's one thing that we're really excited about. And so our target audience is not just first-year graduate students, not just undergrads. It's students who are looking at getting a job in industry that want to teach themselves things. It's professionals who may want to read up on some topic that they're not so familiar with. It's curious high school students that are surfing the internet looking to find out what automation chemistry looks like. So we realized we had a very broad audience, and then the question is how to structure the class to suit the many different audiences. So with that, we discussed it, and we feel that a very modular organization would serve the purposes of serving many different audiences. And the term that was used yesterday at the breakout session was choose your own adventure. So we really want that to be what we achieve with this resource. So we had about 14, 15 participants yesterday, ranging from people working in industry, faculty members, graduate students, and people who run centralized research labs. And we had some really good discussions and got a lot of really useful feedback for fine-tuning our outline. And we're definitely, we need volunteers to help us do this. So at the end of the talk, I'll put a Google Drive link up on the chat if you want to sign up. Alternately, you can email me or email Nikki Pohl or both of us to volunteer. And Nikki, do you have anything you want to add before I go into the details of the 3 sections?
Yeah, I mean, basically, we were also addressing Alon's point of the fact that many faculty members and people who've been in chemistry or the sciences generally for decades also need to learn. And so we definitely saw this modular choose your own adventure sort of textbook, like with videos and everything else embedded, as also a way for that demographic to be able to learn more.
Okay, so as we alluded to, we want a modular type of organization for the online textbook. And for those of you who are familiar with LibreText, if you go in there and look at the inorganic chemistry modules, you can see there's a variety of modules, with a graphic and a description on the front, and you can click on them and go in there and navigate from there. So we're envisioning something like that, and we chose to divide it into three main areas. The first one is concepts, definitions, and methods. So this is the how, this is the why, this is the historical perspective. This is kind of the big picture, so that someone comes in, they want to know how would you design, or how would you do high throughput chemistry for a particular application. They can go and just read generally the why, the how, and then to get more into the specifics of how they do things, how it all comes together. We have a section that we call the unit ops, and this includes hardware, software, analytics. So this is especially good, if someone just needs to get up to date on one particular topic. And lastly, the third section is resources. So this would include links to case studies for teaching, case studies for specific types of chemistry, videos of talks, videos of different types of automations in action, possibly a list of funding sources, just anything that might be useful to people working or learning about this field. Nikki, do you have anything you want to add before we go into the individual topics?
Yeah, so the other thing we discussed was having an annotated bibliography for this. And so if there's interest in this group and from the community at large and help, we'd be happy to also add an annotated bibliography. So in other words, for example, a JChem Ed paper, but a short description of how it might fit into the curriculum and how it might be useful, and annotating it in that way so that it makes it more useful.
Yeah, that's really, something that's people have expressed interest in doing. So the meat and potatoes of the textbook is, especially for teaching, is the section on concepts, definitions, and methods. And one thing that we really want to achieve with this online textbook is to give people a broad introduction to automated and accelerated chemistry. We don't want it to be too specific to any one particular subdiscipline of chemistry. We don't want it to be just pharma or just materials. So we want, we're trying to keep the first section pretty general and touch on the kinds of things that people might need to get up to speed on. So historical perspective, things that, how did this get started? What sort of strategies were used to be used and have been abandoned? And really get into why we want to use it. And at this stage, we'd like to also get some basic computer science and robotic concepts for the students to get everyone kind of on the same page in terms of their preparation, because we are going to be serving people with a range of backgrounds and a range of experience. So we want to have a for beginners section to introduce these basic concepts. And then in the unit op sections, we'll have more information and more resources for people who want to delve more deeply into these. And lastly, we want to get people thinking about some of the bigger picture issues, thinking about, can we use automation to increase accessibility? What are the ethical issues? And I think this is really useful for people working in the field, but it's also, I think, a way to get the students interested in thinking about it and not just have it be this, class on, aspects of chemistry and computer science and engineering. We want to just kind of get them to think about it in the whole and not in the pieces.
Exactly. And there's actually a rich history of this too, because when the so-called microcomputer came around in the 1970s, you can find JChem Ed papers where people were struggling with this idea of how do we bring the computer into the classroom, in the chemistry classroom. So we want to make sure we don't make the same mistakes they made then, and to expand what we can do with this now that the computers are even minier.
Yeah. And so also included in this section are concepts such as design of experiments, feedback loops, introduction to machine learning and how it's not exactly the same as AI, miniaturization, data storage and analysis, and then a bigger question of, how much data is enough, and how does this vary depending on your resources and what you're working on. And additionally, we'd like to introduce people to so-called FAIR principles, a bit of programming basics, and how computers work and how they talk to physical instruments.
And one thing that came up in our discussion was the fact that we want to make sure that we bring in issues of diversity and inclusion from the very beginning of how we think. We want to make sure people developing these technologies think about that at the beginning, not as an afterthought.
Yeah, definitely. So moving on to the unit ops, this is where the choose your own adventure part really comes in. And so Nikki and I did a brain dump of things we thought that should be included in the outline. And then at the discussion yesterday, we got a lot of additional useful suggestions. And so this can largely be divided into 3 or 4 sections. So adding chemicals, removing chemicals, moving things around. It'd be nice to get, modular unit ops on these things, as well as in the resources section, videos of these processes in action. And so this is one area where crowdsourcing is really going to be powerful, because, it'd be nice to, just, have people create 5-minute videos of a solid addition robot, or, a mass flow controller, or, any kind of thing that you might want to use, and just have them there in our resources so people can look. And, I think the barrier towards creating this sort of short content is relatively low. And so we can really benefit from the crowdsourcing. Obviously, another very important area is analysis. And we're going to, I think, keep this content modular as well. One thing that we really like is the fact that this class can be geared towards undergraduates or graduates. So, if someone doesn't have a lot of background with GC type of methods, they can still understand the basics and, go read up on GC if they want. And I'd love to hear feedback from the audience if you have any additional areas and things that you think we should be covering in the unit ops. Obviously, hardware, software, programming, and interfacing are really important. And one of the participants yesterday pointed out that most people don't even don't know the difference between the various types of serial ports, and making sure that instruments can talk to the computers, even after 10 or 12 years when, technology changes. So that's another thing we're going to put in there, and I think will be helpful for people working in the field. And then lastly, we'd like to have some sections on safety and ergonomics. And, this can include safe handling of toxic chemicals. This can include data safety, and then just physical and facilities safety for the instrumentation. And I thank the participants yesterday for bringing this up. It totally slipped my mind, even though I've had flood in my high throughput lab, and I've had earthquakes back in the day when I was in California. So, I didn't even think about it, and I've been through it myself. Do you have anything you'd like to add, Nikki?
Yeah, so you keep focusing on crowdsourcing, which is, I just wanted to emphasize that again. We want it to be curated so that it won't be a live wiki page where you never know what you might get when you assign your class this book, so to speak. But probably at the end of each semester, we'd want to do updates so that we keep this as a live living document. That's the big advantage over a traditional textbook, is that we can link and we can make it a live living document that can be updated every semester, essentially.
Yeah. And then lastly, we want to include a section on resources. This could include annotated list of resources such as case studies, perspectives, reviews, and we want to keep it really, really broad in terms of the types of chemistry. One thing that came up yesterday during the discussions is image analysis, polymer analysis, everything that is of interest to people other than pharmaceutical chemists. And, one thing that's useful here is that some of this stuff is currently being done in industry, but they're just putting most of it into patents rather than into review articles. So I'd love to crowdsource useful case studies that we'll be able to share in a teaching context. We'd also like to include other types of resources, such as computing resources, links to open source classes, other useful links. And during the breakout session yesterday, one of the participants provided a whole long list of really useful resources that he used when he was learning how to code. And we'd also like to include videos, things like the lab in the box, and funding and lists of funding and collaboration opportunities. And we'd also like to get input from the audience to see if there's something else that you think would be a useful thing to put into the resources section.
Yeah, another thing that came up was this idea of version control that software developers always have. They have version 1.0. We don't tend to have drugs or pharmaceuticals that are version 1.2 the way we do with software. We envision this textbook to be similar, which means also everyone contributing gets credit. The people who review and modify things get credit. So just like a piece of software, we expect this to be multi-authored and really a group effort, so that we can give credit where credit is due and also incentivize people to contribute.
Yeah.
So we want to get version 1.0 out reasonably soon, and then it can grow. So we envision version 5.0 to be rather different than 1.0, but we figure we need to get started with something, even if it's small, but mighty.
Yeah. So we really, really need some volunteers to help us do this. So we'd love to get people emailing us if you're interested in participating in a variety of ways. We need content creators. This can, most obviously is people writing sections, but it could also include people creating video content for us. People who are good with creating graphics. If you hate writing and you like creating graphics, please get in touch with us, because we'd like to have it be a well-crafted document and not just like my midnight ChemDraw pictures. And we'd also like people to compile and share existing content with us. So please forward us your useful documents or put them into the Google Drive. And we also looking for people to help read and edit sections, beta test on your students or beta test on yourself. If people have skills with website and platform logistics, that would be really, really helpful. We initially were thinking about putting it on a site called LibreText, but yesterday there was discussion of the advantages and disadvantages of something like LibreText versus a wiki or a GitHub type of platform. There's probably other stuff that we haven't thought about yet. If you have some suggestions, please let us know. And lastly, if anyone is interested in helping fund this, we anticipate it will be pretty inexpensive, but there may be, donation to LibreText might be a good idea, or if we need to get a small amount of editing help, or something where it would be useful to have some funding. So we need help. We're very excited about this project. Please get in touch with Nikki and I to get involved. And Nikki?
Yeah, we'd love to have more people sign up. And also, any aspiring science communicators out there, grad students, undergrads, high school students, anyone. This is also a great way to showcase your work in a curated and peer-reviewed context.
Yeah, definitely.
Yes, and Shane mentions this textbook could also be a good home for information on the experiment in a box that is being invented by the first team. Yes,
definitely.
The list can also mean a lot of ways of learning something is by going to recreating the undergrad lab experiment before you go on to something more complicated. So we definitely see these as linked projects, breakout groups 1 and 2.
I'm going to exit out of presenter mode so I can put the link on the chat.
Yeah, so Louise asked, will this textbook be electronic open educational resources? So that's what we liked about the LibreText, is that it is an open access resource, because we're very aware of the fact that the science is global, right? And it is much more expensive in some parts of the world to buy a textbook than others. And even within the US, that is already a problem. So when do we plan on version 1.0 going live? Anne and I are committed to December, spending a couple of weeks and getting some things together. So it's just a matter of how quickly people also bring us enough content to make a version 1.0 live, because we want at least one choose your adventure path, and then we can start adding many, many other choose your adventure paths. Could we collaborate with the Khan Academy to develop YouTube content? I have no experience. Anne, do you have any experience collaborating with the Khan Academy?
I do not, but I know someone who used to work there, so I will get in touch with her and see if that would be similar to what they can do and if they can help us.
Yeah, we'll look into it. Thanks for the suggestion. The STEM network in the UK may also be worth getting in touch with. That is a great idea.
Yeah. Do that.
Mm-hmm. Because we do see this as a global textbook. iBiology has created an open access textbook for biology. Might be a helpful resource. Yeah, there's LibreText also has many, many great open textbook. If you haven't already looked at that site, it's sponsored by various funding agencies and universities, and it's a great resource for seeing how various people across the world have actually gone about doing open source textbooking. And a lot of this is an equity access issue within the US because of the cost of textbooks and the cost of education. since here people pay for their own education for higher ed. So there's a lot of great aspects of the open source movement that we can draw on.
And if you'd like me to send you a copy of the slides, just message me in the chat or email me later and I'll get you a copy. So moving on to breakout session 3, I'm going to hand the floor over to Shane Krska so he can discuss summary of that breakout session.
Thanks, Anne. Can everybody see my slide? All right,
Yes.
great. So those were some really exciting, 2 presentations, and I think what is really what I really like is just how concrete they are and how actionable they are, and there's a lot of momentum behind both of those. And the focus of our 3rd breakout session was really how do we sustain this momentum? How can we have this not be just sort of a one-off, and then have a lot of excitement for a couple of days and then have that sort of dissipate over time? How do we sustain this? And so that's kind of where we focused our attention. So I want to thank Rob Maleshkin and Becky Matz for co-hosting this with me, and we had a lot of great discussions, and I'm going to summarize some of that for you. So first, just wanted to thank the folks that joined us. I hope I got all of your names off of our Google Doc. If I missed somebody, please forgive me for that. But it was great. I don't know how this all happened. Maybe there was some magic behind the scenes, but this group of people that just sort of self-assembled was such a wonderful cross-section of people. We had folks from primarily undergraduate institutions, from research universities. We had people from funding agencies, both public and private. We had folks from the scientific publishing world, industry folks from pharma, from agroscience and beyond. We had government lab scientists. So it was really quite a great group of people to be brainstorming on this topic. So just want to thank everybody for their contributions. We had some really rich discussions. And I'll just say, as I go along, Rob and Becky would welcome you to kind of break in and help me out if you see anything that I missed or you'd like to add something.
Shane, we also had students and postdocs participate too, which was important.
Yes, thank you. Yes, thank you. I forgot to mention that. So excellent point. And in particular, the students' perspective was very helpful. Especially as we were trying to connect into some of the fundamental needs, the felt needs that folks who are kind of coming up through the education system and what they're experiencing. So our focus for our discussions were really around trying to set our eyes on what some sort of consortium, or there's maybe a different term we could use, a structure that could continue to bring together people from industry, academia, funding agencies that would advance this goal of democratizing chemistry, and specifically through the use of automation in the educational setting. So that was obviously a very grand objective, and we didn't imagine that we would be able to solve that in an hour or so. But that was where our conversations were. That was the line of sight we were trying to keep in mind. So the way we sort of broke our time together down is we had 3 separate discussions. We had 3 different teams. So we had small groups of folks that really facilitated conversations. And the first exercise we did together was we looked at a straw man problem statement, which I'll show you on the next slide. And the point of that was just to kind of reactivate some of the memories from the morning's presentations, to get folks really thinking about what are our big picture goals and aspirations. Why are we doing this? What is the problem we're trying to solve? And then once we had sort of that thought in mind, the next exercise we did was really around sort of inventorying what are our assets, physical assets, human assets, financial assets. What are things we bring together collectively as a community to address this challenge and this opportunity, but also what are some of the things that we need to overcome, some of the roadblocks, the hurdles that are in our way. And then the last session that we had in these breakout subgroup teams was just brainstorming, well, how could we get started? What would be some concrete, first steps that we could take? So I'll take you through each one of these. And again, welcome Rob and Becky to jump in. So I won't read this entire problem statement, but I think it's actually posted in the agenda somewhere. But basically, the gist of this is this idea that exposure to automation in the undergraduate and graduate curricula is pretty spotty, uneven, and in many cases non-existent. And this sort of heterogeneity creates some gaps, both in terms of training our future workforce, but also could potentially lead to a magnification of differences amongst folks coming from different backgrounds, different educational institutions, and that could really threaten our efforts to be more inclusive and diverse and equitable in the chemical sciences. So that was where we started from. And we asked people to just interact with that, to challenge that, to tease that apart, to maybe replace certain words, to amplify certain things. So it was actually a really good exercise. We really got the brain juices flowing. And so, just to summarize a few of the ideas that once we all kind of came back together at the end, that sort of bubbled up, and there were many ideas. But some of these things are reinforcing some of the themes that we already heard this morning. One is that, rather than being too fixated on getting people to actually have their hands on some automation equipment, in a high school setting, perhaps what's more important is to be exposed to the value of automation and also the concepts behind it. And again, I saw a lot of that, emerging in the first two discussions we had this morning. So that was something that was a nice way to reinforce, that we're kind of on the right track here. The other sort of train of thought that happened is that our problem state is sort of focused on a negative, presentation of the situation, whereas actually there's a lot of upside to this. And if we get this right, we're just opening up access to so many more people to our field. It's just so exciting. And again, this kind of harkens back to some of the great discussions that we heard yesterday from Nikki and Marty, all the collective brain power of 7.5 billion people, but even, thinking more locally, just, folks who maybe for one reason or another don't have access to, really state-of-the-art laboratories, or maybe have a physical disability that would preclude them from, participating in certain types of experimentation. So there's really a great opportunity there for our field. The third bullet, which I think really came through loud and clear, was the importance of being intentional. It's great to have excitement. It's great to have lots of ideas, but what is needed is commitment to follow through. And again, I think that's why it was so important to see how these first two initiatives that we talked about this morning actually have some pretty concrete action plans and intentionality that they're actually going to do these things. There was even some mention that there's been some previous sort of workshops that have been on this topic that, again, generate a lot of excitement, but perhaps nothing really significant or concrete came out of it. And so, are we going to get it right this time? So I think that was a really a powerful point that came across. And then the last point, which I found very inspiring, was just the idea that automation is sort of a gateway to cross-disciplinary research and training. And there's a really great kind of back and forth between those two, that by embracing this, one opens up a lot of opportunities, but also one can use cross-disciplinary research as a means of justifying why we need automation. So did you have, Rob or Becky, is there anything you want to add to that?
No, I think you covered it well.
Yeah, same.
Okay, great. Okay, so then moving on, the next exercise was sort of the inventory. And on the sort of asset side of the balance sheet, again, lots of great ideas out there. I'm just summarizing a few. but just kind of grouping them together, one of our big resources, not surprisingly, is our people. And that's why, I think it was on clear display in the first two talks was, how do we unlock all of the knowledge and experience and wisdom that is out there in our community already, and how do we get that out to where it can actually help others learn how to use automation, get excited about automation, and get enrolled in this. So, that was, something we felt that we really need to be thinking about how we unlock all of that potential across industry, academia, government labs. And again, just the power of bringing people together from different disciplines, not just chemistry, but engineering, software, data science, et cetera. Another kind of interesting point that was added into there is that if we want to be successful in bringing people together and having focused, sustained effort on this problem, and not again just have one or two projects then have it kind of go away, is there's a lot of expertise in for example, like an industry around project management, or we could talk about administrative skills. And so there's really a strong need to organize all these efforts and keep them coherent and manage timelines and manage deliverables and communications and knowledge capture and all of these things that are so important, right, to a large kind of multifaceted effort. So I thought that was a really great add there. And then I guess, another sort of category of resources that we spend some time talking about is just funding, and the idea that, because we're operating in this particular arena around education and workforce development, that we can start to think more holistically and more broadly about looking at funding streams that may be beyond the typical ones that we think of in science. And so, there's a big opportunity there to connect to others in the field and start to brainstorm around where we could find additional sources of resources and support. Becky, Rob, anything there you wanted to add?
And I think you covered it well.
Okay. All right. All right. And then on the sort of roadblock side, again, amongst many things that were mentioned, one of the big ones, at least thinking in terms of getting more folks from industry involved, is that there is a perception that this is sort of a nice to have, like something, maybe you do this in your volunteer spare time. It's difficult perhaps for some people to spend significant amounts of their time on this, and perhaps industry is still kind of waking up to this idea of workforce development and really making these kinds of investments in training and in bringing in more inclusive approach to bringing people into our field, as seeing that as a business imperative. And so I think there's still work to be done, and we talked about some creative ways that scientists could work with D&I type offices within corporations to try to maybe move the needle on that. Another perceived roadblock was around intellectual property and the sort of contractual complications that come with that. Again, probably a lot of that's going to be dependent on the scope of the activities we do. If we keep it in the educational arena, probably a lot of that will be much simpler to deal with. Another roadblock was identified was just the idea that we're challenging the status quo when it comes to how we teach synthetic chemistry. I think that's been mentioned a few times. Another one is just, sort of people's perceptions that automation is difficult and complicated, and that, we need to make it easy for folks, make it accessible. And then finally, the sort of cost issue. And again, that comes down to how we simplify this and how we really think about connecting with people where they are. Rob, Becky, you want to add something?
Yeah, I mean, I think, in terms of the different perceptions of automation, this is one that I think it's really important as we go forward that this consortium works to recognize that to introduce automation into the curriculum, we don't have to duplicate what Anne has at Cornell or what you have at Merck. And I think this is something that the consortium can really serve to crystallize the ideas that automation is a great tool to teach cross-disciplinary education, to teach students how to actually do experiments where they can get data and make a decision on the next experiment based on those data in a way that's economical, but that doesn't require a whole giant infrastructure. And I think this is something that that the consortium and those interested in this really need to stress.
Fantastic. Yeah, thank you. Good. So we wrapped up our discussions with, actually, I thought this was my favorite part, was really in this kind of brainstorming mode about, okay, this is great. We kind of have our minds wrapped around the problem, but where do we start? You know, what do we need to be successful? How can we really have something that we could establish and have some staying power? And got a lot of great ideas from people. And again, just a few of them are captured here. And you know, we intentionally kind of structured our time this morning to leave open plenty of time for folks to ask questions and you know, suggest ideas. But one of the ideas that really kind of stuck was that this whole effort needs to have a home. It needs to have some kind of sponsor that it has credibility and visibility, that can sort of bring that additional kind of, you know, accrual of energy and enthusiasm. And, you know, so there were ideas around government sponsorship. But one idea that was kind of intriguing, I will say, to most of us, was the idea that perhaps the academies could serve as a home. And so we spent some time talking about, you know, could we possibly charter a new roundtable that would, you know, be a focused roundtable on this initiative, and it would be cross-disciplinary, and it would be, you know, its charter would really be to further these goals that we've been talking about here in this workshop. And specifically, it would be to deliver on the open source textbook and the automation in a box. And those would be the first two kind of big wins that this roundtable would go after. So that was, you know, definitely something that garnered a lot of enthusiasm in our discussions. A second point was, and again, we heard this in earlier discussions, was we need to get traction right now. We need to capture the momentum that we have from yesterday and today. So creating some kind of like a Slack channel or some place for people to interact digitally and to draw in additional people and enroll them in this, a place to post ideas and comments, and, you know, coming up with a database of funding sources, or, you know, you name it. We need to have like a unified place where we can all continue to interact. So I thought that was also really creative and could be easily implemented. And then that last bullet, I guess I sort of mentioned that, is just, you know, the number of people who've been involved in this workshop is really encouraging, but probably a relatively small fraction of those who could be involved. And so probably many of us know others that we are already thinking about reaching out to, who could help us in this journey. So that's kind of our big summary. And I think, you know, again, Rob, Becky, if there's anything you wanted to add, otherwise just kind of wanted to open up the floor and get people's reaction to some of these things.
I mean, the only thing I'll add is that this is, I mean, we got to get who is going to be participating in this consortium to continue to move forward. But there will need to be some strategic planning. The consortium can't get, needs to have a certain level of focus on whether it's simply helping to deliver, you know, the open source textbook and the automation in the box. Maybe it's just that, but maybe it is something bigger. But we do need to have a strategy, and I think that's got to be a step along the way.
Great point. So we didn't include any specific links, but, you know, I think for those who are interested, you know, I think it'd be great for them to reach out, you know, to Rob and Becky, myself, or even, you know, one of the conference organizers, you know, for example, Linda, and just, you know, indicate your interest in being involved. I think actually, maybe Rob, Becky, just occurred to me, we had that little survey. Is that something that we could potentially have a link posted for folks?
Yeah, for sure. So this is just like if you're interested in being involved in follow-up discussions, you can just kind of drop your name there. So I'll drop it in the chat.
Okay, that'd be great. Curious, I mean, any reaction from folks to we tried to come up with a little bit of a concrete proposal. We're trying to be a little provocative here. Any thoughts on this? All right. Right. So thank you. Eric mentioned that there are some pre-competitive collaboration consortia, the IQ and the Enabling Technologies Consortium. That's great. Yeah, we could certainly learn from some of those models. And yeah, excellent. And Alan mentioned the Acceleration Consortium. So one of the discussions we had was around the scope of this, and whether it's mostly around an educational focus, or whether this could expand to include sort of a research component. I think we were thinking that initially it would make sense to have more of this sort of educational workforce development focus, but again, interested to hear what others think about that.
That's Jar Bayodi from P&G. May I offer a comment to your question?
Please. Thank you.
Yes, I was thinking, I understand education is very, very important. I look at another vantage point, which is the chemical enterprise as a formidable challenge and opportunity in front of us, sustainability being one, where we will need to replatform materials that have been commodities to new materials, which means we'll need to compress in a matter of months rather than years, or years rather than decades, the innovation. And I was just thinking with what I heard yesterday, right? Automation and AI together on high throughput will be necessary for us as a chemical enterprise to do our mission. Like someone mentioned yesterday, the genomics, we take for granted that PCR is automated. If PCR was not automated, we will be in a different place in terms of health and wellness, and you name it. So I'm wondering whether there is another vantage point, that is to say there's a grand problem that is of interest to academics, White House, national agencies, and industry, and we create a consortium. So I may be off track, but I was just saying that could be another one where maybe it's the right time to look at. This could help solve big problems, and it cannot just be a single university or a single company. Sorry, Alan wants to say something.
That's great. Thank you.
Yeah, sorry for plugging in, but Gerard, I just sent you a DM. We're trying to do that exactly at the University of Toronto, a global consortium on that. So check out acceleration.consortium.ai. Our mission has educational components. That's why we didn't want to pick this up completely, because it's beyond our capabilities. But right now, really what we're building is the industrial aspect of it. And we have several companies signed up already, as well as about 60 academics. If any academic in this room also could like to be part of the Acceleration Consortium, send me a DM, and we are constantly adding new people. It's kind of like a join if you're interested. So check out our website. There's a new website coming up also, but there's about 5 corporations that are going to start as founding members. So please reach out if anybody from the industry wants to learn more about it.
Spot on. Thank you, Alan. I learned something big today. Thanks.
That's great. Yeah, thank you. Excellent discussion. And that's a really, it sounds very exciting. And again, I think there's a lot of room here for complementary efforts, right? Excellent. Any other thoughts? Didn't want to cut off a discussion that seems to be picking up speed.
One thing is, so I agree with the educational mission and for the consortium. One thing that I didn't see that might be useful is getting the analytical instrument makers involved and having expectations for software performance, integration, compatibility with both human and robotic platforms. And since I don't think they're here, it's maybe not fair to sort of plan all that, but some way of communicating with them general expectations for what we hope will be compatible with these automated autonomous systems.
That's great. Yeah, thank you, Benji. I think that's really important.
Let me also add that, yeah, I think involving vendors is absolutely essential. And as this was being planned back in the old days where you actually went to meetings, I actually was at the American Chemical Society meeting, and I surveyed a lot of the vendors at the expo. And perhaps not surprisingly, a lot of the smaller vendors were really very excited by this, and really, I think, would be great partners and participants in the consortium. Some of the bigger vendors didn't seem to be as interested, but that can change. But I think vendors are really important. And I do think, again, based on an unscientific walk around the expo, that you can get a lot that really do want to partner with us on something like this.
Fantastic point. All right, any last comment before we close? I think we're at time. Awesome. All right, well, I want to thank everyone for this morning's session. It was really stimulating, and it was great to see how these ideas are kind of all resonating with each other. Thank you all for your contributions. And I guess now we're headed to a 15-minute break, and we'll see you all back at 10:30.
Great. Hi, everyone. Hope you all had a nice break. Our Dr. Arsalan Mirjafari will get us started for the second part of the workshop.
Thank you, Linda. Hello, everybody. Welcome back to session 3, the promise of automation. We are going to have 3 wonderful speakers. So we start from Professor Alan Aspuru-Guzik. He's a professor of chemistry and computer science at U of T, University of Toronto. And his research is in the interface of the quantum information, chemistry, machine learning, and chemistry. He needs no introduction. Thank you very much, Alan. The Zoom is yours.
Thank you. I'll share my own slides if you don't mind, and hopefully people can hear me. Setting up a timer for 20 minutes also, so that,
wonderful,
like we are also on time.
Just letting everybody know, at the end of Alan's talk, we are going to have time for 1 or 2 questions.
Yeah, so let me just make sure I use the time quickly. So I'll tell you a little bit about my perspective on self-driving laboratories and how I think everything goes together. So we've been discussing, of course, in this workshop, automation, but automation is a bigger piece as well, of course, together with AI, to what we like to think about as closing the loop, which basically means really deciding what's the next best experiment to make based on all the previous information that you have in terms of your data gathered by the experiment. There's a couple of differences between this and high throughput virtual screening or high throughput experimental screening that probably were covered already previously in the workshop. But needless to say, it is the usage of all the data in real time what makes it much more efficient than just high throughput experimentation. Of course, it requires tons more integration. So this was already part of this puzzle, has already been recognized by MIT Technology Review last year. I feel partially responsible because I'm associated with my startup Keborex. I collaborate with In Silico Medicine, and my 2 institutes are mentioned. But I think this was highlighted because even though I worked in many other fields in the past, for example, quantum computing and other fields, this is my most cited paper now, and it appeared in 2016 in the archive. And what it is basically an autoencoder approach to doing inverse design. Okay, so how can you encode and then decode information into a neural network latent space, couple it to a property, and then use the property predictor to backtrack which molecule or material is a material that you want to optimize. So this is AI discovered molecules, one of the pieces of the puzzle, right? It was realized already by several laboratories. This paper by Alex Shaborankov and In Silico AI, I'm a part of it. In 46 days found a DDR1 kinase inhibitor. There's also work from MIT and work from EPFL and other places, as well as other pharma companies that are working on this space. This company In Silico now raised $550 million, and it has a compound in clinical trials based on this technology. So this is not just whatever, like this is not just out there in the sky. This actually has been demonstrated, for example, in these cases. What is the state of the art? There's many groups working on this all around the world. In terms of the AI generative models aspect of this, from my own lab, and I'm using it as an example throughout this talk, obviously recognize the work of many others in this room and others. We collaborated with Randy Schnur and many others in the Nanomaterials Genome Center, funded by the DOE. We basically built an autoencoder that generates compounds as potential MOF candidates. And we find it as challenging because it's not neither a crystal in traditional sense nor a molecule. It's this periodic material with molecular fragments and also metallic fragments, many topologies. And it's remarkable that it proposes so many good compounds. So you might say, okay, this is it, Alan, we're done, let's go home. But obviously part of this workshop discussion and core to it is the fact that generative models, in my estimation, will only give you a factor of 2 or 3 in terms of the discovery process, if any, okay, at least in my own experience. Because really the bottleneck is, what do you do with those predictions? You have to actually integrate them with experiment. And therefore, we call these things materials acceleration platforms. Benji in the room also calls them self-driving laboratories, many other names. But basically what they are integrated, an integrated data acquisition, experimental execution, and AI, as well as high performance computing tools. Please check out this report that we wrote in a workshop organized in Mexico. I think has been seminal to the field, and of course 50 other scientists and I wrote it, so was co-led by Christine Persson and myself. So I recommend you guys to check out that particular workshop report. So I'm gonna just use examples. Actually, Marty, one of the leads in this conference, Bartosz, Lee, and Jason and I are funded by DARPA in the program of Ann Fisher. And I want to use it as an example because we're trying to find a new molecular class called organic lasers, just proposed as a feasible class, solid-state organic lasers in 2017 by Chihaya Adachi. You can read why they're useful there. And for that, we're using the automated methodology of Lego block synthesis by Marty, present in the room, which basically is employed by nature to build all these biomolecules you see on this slide. Here are some examples of Marty's chemistry applied to real life. I like this because there's a kinase inhibitor, like I just told you, that we discovered one with AI, and also organic materials in the same slide. Having said so, this chemistry is not just a plug and play. You need to actually optimize it for the problem at hand, and this collaboration has been doing that. Many more news to come, that I'm not going to steal the thunder of anybody. But what I'm going to say is that crucial, to the discussion in this workshop is the fact that to make a self-driving laboratory work, you have to really be multidisciplinary. I had the luck of having a very multidisciplinary group and multidisciplinary set of collaborators. But for example, in this case, you need to have fundamental physical chemistry knowledge of the molecular properties that you require to make an organic laser. This is not a lecture, but rather a small 20-minute presentation, so I'm going to skip the photophysics. But needless to say, if you have a photophysics model of the lasers, you know what are the processes you want to maximize and the processes you want to minimize. The other thing that I want to say is that you don't necessarily need retrosynthesis. In this project, we think about the forward synthesis chemical space of accessible compounds to the robot. That's going to be the space that we're going to push forward and explore. And for that, this is where our colleague Bartosz Grybowski comes in. His collaborations come in many different aspects of this project, but one of them is, for example, the use of AI to filter out which reactions will not happen. That way you can prune that combinatorial space, and the only molecules that you actually search with quantum chemistry, shown here on the right, to actually characterize their laser their potential properties as organic lasers, are the ones that you will later go and do in experimental testing. The platforms vary. There are many platforms involved in this: the computer of Lee Cronin, the machine of Marty Burke, a Chemist system that I'll tell you about today, and Jason Hines systems. Roughly, the experimentation is in tens of experiments per day. It could go to hundreds because we need to build a significant amount of material. So this is a little bit different than drug discovery. Again, just emphasizing the physical chemist in the audience, automating the calculation of biblionically resolved absorption and emission spectra is crucial to the success of this project, as well as automating workflows for quantum chemistry that allow you to have rapid screening. So there is a role for everybody to play: the fundamental physical chemists, the quantum chemists per se, the computer scientists, the chemical engineers, the chemists, etc. So I think that's a very important aspect to emphasize. In this case, for example, the correct calibration of tight binding DFT allows you to run calculations in minutes that will take hours otherwise. And again, this is just a picture of all the variety of systems. I mean, there were discussions, as I hear from yesterday, on how to make this thing universal. None of these things will be the final product. But what is really nice about our project is that we integrate the best knowledge from different ones and transfer technologies across laboratories. So this has been extremely helpful. I do have, for example, a machine from the group of Marty in my lab running, and we already have made some hacks to it. I mean, we kind of optimized a few things and made it easier to use in certain aspects. Definitely we get from them something, and we're going to send them back soon also some improvements. So the system that will allow us to do high throughput search of these lasers is shown here. I like to think about it as an organic chemistry lab coupled to an analytical chemistry lab, coupled to a physical chemistry lab, run by a theoretical computational chemist. So that's what we call this madness, right? You can see it here in the back. The ChemSpeed synthesizer comes out with the multi-step mid-aboron coupled protected Suzuki couplings. This thing does the HPLC EMS, does the separation and the semi-prep purification. That it eventually comes into this diluter here that we built that allows us to do photoluminescence experiments, and then as well as time resolved CW, and also excited state absorption that you cannot see here on the right-hand side, another optical table there, or optical piece of the table there. So this clearly has been a lot of time to build, a lot of money, but now it works basically. We spend a lot of time using AI to calibrate the dosing and dispensing aspects of these robots. A lot of chemical development together with the group of Marty and the group of Jason and Lee, as well as Bartosz. And then, of course, the use of other robots. Actually, this powder dispenser is finicky, so we actually have another powder dispensing robot. So in other words, this field is pretty complex, but I think with the right multidisciplinary team, you can do wonders. This is kind of like one of the benchmark studies, a collaboration with Marty, where we ran 40 compounds on a weekend and optimized their properties. And we found in this particular molecular class, best-in-class molecules with lower photoluminescence lifetime and highest relative quantum yield at a color that is desired for organic lasers. They're being characterized in Japan, but this is probably the most exciting slide for a theoretical chemist to show you. One automated system synthesizes, characterizes, and is computer-driven, all of it in a single shot. So we're not in 24/7 production mode yet. We budgeted and we started working on that probably at the beginning of the next year, because the maintenance of the systems and the running them 24/7 really requires a lot of learning. And we finally think are ready to do that. So in the remaining part of this talk, let me just tell you a little bit about, I think, what I consider the most important aspects of the AI-driven aspect. Basically, our open source ChemOS software allows us to control the experimental setups. And I really want to spend some time evangelizing or talking about the importance of thinking about Bayesian optimization. Okay, this is very important to think about what are going to be all the different tools that you're going to employ to optimize the conditions for your experiments. So my lab and others, of course, have been active on this field. For example, Alexei Lapkin in the UK is very active. Christopher Reyes also has some interesting work. What we do in my lab is develop these tools: Phoenix, Chimera, and Griffin. These are the mainstay tools. A continuous variable optimizer, a categorical, which is choice optimizer, combinatorial optimizer, ligand 1 or ligand 2 or ligand 3 or fragment 1 or fragment 2 or solvent 1 or solvent 2, as well as a multi-objective Pareto optimization function that basically thinks like a chemist. It says, I want to try to satisfy one objective, then jump to the next objective, then jump to the next objective. I gonna emphasize that it's the use of these three tools together that allows us to do practical and efficient optimization with several collaborators around the world. There are new developments that I'm highlighting here. Golem just came out in chemical science. And in conversations with Merck USA, we we found that there is uncertainties in the factories. This is for process chemistry. So how can you optimize processes where you have uncertainties on the parameters? Golem allows us to do that. And it's also plug and play with the 3 aspects before. Of course, multi-fidelity optimization, cheap variables, predicting expensive variables, another paper that is on the archive right now, as well as benchmarking tools like Olympus that allow you to compare all our algorithms with everybody else's algorithms and use the best one. Like, by no means I'm going to say that all of what we're developing is the best. What I'm saying, we should compare it, and that's why we developed Olympus, so that everybody can put their algorithms in their data sets and we can all share. So Olympus is a repo that everybody can add their algorithms, their data, and we can certainly compare notes with everybody in an open access manner. If you think like a chemist, you can beat the computer scientists. That's the punchline. And what do we mean by that? By using chemical descriptors, which we chemists know and love, we can deform the categorical optimizer metric in such a way that the categorical optimizer knows about HOMOs and LUMOs, okay? And therefore, 2 molecules that have similar HOMO and LUMO in this particular organic photovoltaic example will be considered similar. Therefore, the optimizer will not evaluate them together. They will only evaluate them once, roughly. And therefore, we have, as we call it in computer science, state of the art, we believe, in optimization of chemical matter, because these are the best optimizers from the computer science literature. They require about 11% of the space to solve this organic photovoltaic problem. And we're able to do that this is a computational study, basically, but we are able to do that in 7% of the experiments. So in other words, if you have a 4,000 experimental space with about, in average, 7% of those, you will be able to actually reach out the optimum. There are real-time examples. For example, this paper in Communications in Chemistry is another ChemSpeed optimizing the E/C ratio of a catalytic reaction. After 200 experiments, ChemOS doing a categorical optimization, and this is, by the way, led by Mellon Christensen in collaboration with a group of Matt Sigman, and the main group that did this is Jason Hine. So collaboration with Jason, what we contributed was the ChemOS, Phoenix, Chimera, and Griffin approach to be able to help find this categorical and continuous variable optimization problem. Here are the set of ligands that I use for this Suzuki coupling, as well as the different experimental conditions associated with this particular reaction. So this is an example of how we can actually move the needle in this particular field. There's also the role of computational databases. As you guys know, the Materials Genome Initiative succeeded, but also failed, I think, in the sense of emphasizing databases and not emphasizing the entire workflow that we're talking about. But having said so, of course, databases are important. So with Matt Sigman, we developed this database that basically contains hundreds of thousands and even virtual libraries of millions of compounds, which are basically phosphine ligands for Suzuki coupling. So this particular Kraken database, I think, is going to be very useful when we actually couple it to the robots to actually design and select ligands for a particular Suzuki coupling. So all of these pieces come together. The last thing I will mention is the cost of synthesis. We have a new way to actually cost out the synthetic aspects of robotic and human synthesis together. I'm going to skip a few slides. Needless to say, if you couple that particular costing algorithm with Chimera, this objective setter, you can design organic lasers where you first pick the color of the laser. Second, if you satisfy the color, you move to how easy it is to synthesize. Finally, how well it's going to work as a laser, which are these 2 last properties. So this is a 4-level Chimera optimizer. So it's optimizing 4 different functions together. What we find in this particular experiment is that region in blue are easy to synthesize molecules between humans and robots that are also high performing, and the region in red is molecules that are very good performers but hard to synthesize. You can see there's like 2 maxima there, and if you actually use the ease of synthesis in your screening as well, then you will only actually test in your robot things that are easy to make, and that's going to be so important. I'm not going to emphasize how much important I believe this particular aspect is going to be for the future of our field. And finally, if you really want to think about the future, you're going to start thinking about computer vision, AI for picking up glassware in particular random positions, I'm gonna skip this. But basically, our lab is very active, building robotic systems that can pick up transparent glassware from anywhere to anywhere. And basically, this is done by creating huge data sets and by actually using robotics knowledge, collaboration with computer scientists. I advertise Acceleration Consortium. Please send us an email if you're interested in working with it. There's a lot of things that we're trying to do globally in an open fashion, industry, academia, and the government together. And I only have 1 more minute left, so I will advertise one last thing. We also launched a journal together with the colleagues I'll show you in the next slide, which is called Digital Discovery from the Royal Society of Chemistry. I recommend everybody to send us their best papers because it's gold open access. We have a fair reviewer that only looks at data. We want to have all your open data sets. We have open, transparent peer review. I was very proud to see that ACS Central Science announced this after us. Yeah, just a little jab at them, but we were first. And this is the editorial board so far, and we're very proud of our diverse and young and energetic editorial board. So please send us your papers. And I just ran out of time, so I'm happy to answer any questions you might have.
Thank you, Alan. Any question?
I do have a question. That Gerard here.
Go ahead, please.
I did not raise my hand. This is fascinating. Really great to see the advances holistically between AI and chemistry and robotics and analytical. May I ask the $1 million questions, which is polymers, right? Do you think, Alan, I mean, clearly there are some complex, I will call them small molecules, probably translatable into AI. The big, opportunity and challenge for us in the industry, and when we think about sustainability and surface modification, is polymers. Could you comment on when polymers will be integratable into, the discovery machines that you are sharing with us?
Very good question, Gerard. Let me just begin with catalysts. With the Natural Research, NRC, National Research Council of Canada, we have a robotic system already working for OER, oxygen evolution reaction catalyst discovery. That is built. For polymers, we requested money to the Canadian government for another system. Right now, the request is open, but if the system comes in, we'll be buying a ChemSpeed polymer synthesizer. We don't know how well it's going to work. We have learned from the ChemSpeed systems require a lot of work. But I think because we stood up already the small molecule one, we're going to start exploring the polymer one as part of the consortium efforts. And I bet you other groups around the world are also advancing this area. So Linda also asked about polymers. I think they are the next frontier. Collaborators in Northwestern University want to do ChemSpeed. They already ordered a ChemSpeed for MOFs. So I would say, at least through our consortium, we can see all the academic groups that are doing different aspects of this, and also the industrial groups. So I think polymers are coming. Gerard, maybe we're 2-3 years behind compared to molecules, but definitely Dwight Ceferos in Canada is going to be pushing this effort in our consortium. And happy to report to you how well we do, but definitely this is an area of tons of interest to us as well, due to the circular economy and the pollution of the waters in the oceans and all of that. We need to think of new polymers.
Thank you, Alan. Terrific.
Any other question, everybody? We have 2 minutes. So, Louise, go ahead.
Yes, Alan, thank you so much. I've heard you mention MOF synthesis. My question for you, after you produce MOF, do you have a means to predict the, say, surface area, internal power size?
I just showed you that Nature Machine Intelligence paper of ours, so we can generate candidates where we can actually post facto look at our samples and measure that. So our generator is very fast. So I think the answer to your question is yes. I think what is challenging more is how to develop an experimental workflow like the one I just showed you that actually makes them off based on the molecular linkers and the metallic fragments. And I would like to say that the hidden cost of all of these materials acceleration platforms, so self-driving labs, is the cost and time to set them up. They will be rapid once you build it, But my experience is building a map will take 2 to 3 years between procurement, setup, and testing. And then once it's ready, then you can fly, as many of my collaborators do. Like Marty Burke's map flies, but he could probably agree it takes a while to set them up and debug them. And that's the challenge that we will face with MOFs when Omar Farha starts setting up his robot and we help him.
Okay, thank you.
Thank you, everybody. So thank you, Alan, for a wonderful talk. So I would like to welcome our next speaker, Professor Joe DeSimone. So Professor DeSimone, I'm sorry, is a Sanjeev Sam Gambhir Professor of Translational Medicine and Chemical Engineering at Stanford. So his research focuses on the green chemistry, medical devices, nanomedicine, 3D printing. And he's been founder of the several companies like Carbon. And thank you, Joe, for accepting to give a talk and sharing your thoughts and wonderful science with us.
Well, thank you. Thank you. And thank you for the invitation, Linda, and really appreciate it. And I think when Linda contacted me a year ago almost and talked about joining for this very important topic, and I pushed back a little bit. I said, and my former postdoc Andy Cooper is in this field and is a leader in this space, and I sort of felt like I am not in this field, but I've got a tangential experience that I think may be worth sharing with everyone, in perhaps a diversity of perspectives. So let me share some slides, and then even in the last week, I changed what I was going to say. Based on the symposium here. So can you see my slides?
Yes.
Okay. So the title, food for thought, digital manufacturing is here. Shouldn't it tie into upstream laboratory research automation? And that was sort of what I was sort of reflecting on. But I think, and maybe before I get started, just want to sort of run through my group. And, I've got students from material science, bioengineering, mechanical engineering, chemical engineering, and chemistry. And so it's covering a pretty wide range. And I think, we just heard a lovely talk about the diversity of disciplines needed in all of these fields. And I strongly support that. And then, this has been something that I had the privilege of stepping away. So one interesting thing about this workshop and this topic is there's a lot of people thinking about companies, it seems like. And I stepped away from the university to start a company. I promised the investors, well, first of all, I told them I didn't want to do it, but they asked me to lead it. And then I agreed to do it for a year and ended up doing it for 6 years. I'm not advocating that for everybody at all. It's a lot of work. If you want to talk to me more about that, I'm happy to do that. But I've gotten a lot of experience in launching a company. And in addition to that disciplinary diversity, I think it's also important to be clear about your values so that you can be a destination for excellence across all different corners of the globe, and encourage you as you move these forward to be thinking about those dimensions. So the company I launched is called Carbon. We do 3D printing. And it's really at the end of the day, we help customers bring new products to life. And it's a transformative way of making things using light instead of molding. Kind of like lithography and Moore's law for the last 50 years, but this is pattern light that makes three-dimensional objects as opposed to two-dimensional layers. And those of you that are moving into this space, I just sort of want to share some perspectives. I don't want to scare anybody, but I think launching a software company is pretty easy. And, and this is a happiness quotient versus time. And everyone's enthusiastic in the beginning, and lots of enthusiasm goes up. The trough of sorrow emerges after that, and you end up experimenting and pivoting, and eventually you get happy again as you scale. This is way harder for a hardware company. And a lot of you are at the interface of software and hardware. And I just want to prep you in that this is not for the faint of heart. This is way harder, I think, and a lot of people do. My friends, Andre Yosefi, who put this slide together, this is a hard world to live in. And it's even a harder world to build a business, a sustainable business. And I want to reflect on that aspect a little bit. But again, I'm going to come back to people. This was us launching our prototype printer, which was more like a glorified toaster in the beginning for making 3D printed parts. But the man there in the blue shirt, white stripes was Craig Carlson, was our founding VP of engineering. He was a founding VP of engineering at Tesla before Elon bought in, and he brought out the Roadster and the Model S. And we had over 50 ex-Tesla employees with us at Carbon. And I'll come back to what that means. But at the end of the day, this is all about people, and the challenge, the science and the engineering won't be as hard as the people issues. Repeat, the science and engineering won't be as hard as the people issues. Getting people to work together from different disciplines. This was the software team on the left. That's a crazy crowd compared to most. And getting all these different people working together is really the essence of this. And this is what it's like launching, additional new products all the time. So, one of the things that you're all doing, it seems like, is this integration of hardware, software, and materials or molecules. And polymers are molecules, by the way. So I know somebody mentioned that earlier, but integration of these. And I think one of the questions I have for you all, and I encourage you to think about this deeply, is this statement here. Is that how can your early customers, your early partners, join you on a journey with the confidence that they are future-proofed from obsolescence? In other words, they're going to pay for stuff. And they're not going to worry about it. In other words, that they're going to benefit from your advances in a way that allows them to grow as you grow and advance. I want you to think as much about the innovation in your business model as you're thinking about the innovation in your science. And this is critical so that you actually can be a sustainable, growing concern. Because, vision without resources is a hallucination. And so you need to have these models together. You got to be thinking deeply about this. And for us, the thing I was most concerned about was somebody paying for that toaster I just showed you and being mad the next day when we introduce a better product. I didn't want that. And I wouldn't want somebody to do that to me. How do you get people to invest in what you're doing and recognize that they're going to grow and advance and not have to worry about the sunk cost? And so what we did is that we introduced a pioneering technology and a pioneering business model. That was not just a business model, but it was a technological decision that we made related to smart hardware. We designed the hardware out of the gates to include an extensive use of sensors and control systems using the principles of mechatronics. And the idea was that, so mechatronics is this merging of, it's what the Tesla is made from, that mechatronics engineering. It's a fusion of mechanical, electronic, and electrical engineering. Everything is sensored up. There's no dumb hardware here. It's more expensive to launch hardware like this, where every valve, every sensor is tied into a overarching software control system. And it allows one, especially using open source approaches, to allow the printers and the process to be infinitely upgraded and improved with over-the-air software upgrades. So that the more people use the technology, the better it's getting. And it's an intimate partnership ultimately with your customers and partners. This model is an engagement model. This is not a transactional sale. These are partnerships. And if you do this right, you end up with a cult-like following because you're a team and you're working together. And the improvements that you learn about, you can pass on to your customers. And so there's a network effect. The more people that use your technology, the better it gets, right? And that helps you to scale. So to me, these are some of the tenets out of the software world, right? You know, Mark Benioff, when he introduced Salesforce, he positioned it as the end of software. What he meant was it was the end of the box of disks that you get, right? It was all cloud-based software, and it was constantly being upgraded, and you didn't have to worry about it. And so then you wrap this into a subscription model, right? That you end up having people join you and they're paying you a subscription as opposed to a transactional sale. This often requires a little bit more capital when you launch your businesses because you're not making your profit on the sale directly, but you're building a sustaining base of customers and partners that grows with time. And very often, you know, our subscriptions came out of the gates at 3 years, 3-year commitments. And so that gives you a lot of stability and planning opportunities on funding because you've got a stable source of revenue that grows. It's kind of like an install base. Manage the business like you manage windmills, right? And you're just building an install base and a partnership. So I wanted to leave you with that point. My partner in crime in thinking about this was Alan Mulally. Alan was the CEO of Boeing Commercial Aircraft. He's also the iconic CEO of Ford Motor Company. He's on my board at Carbon. He's on the board of Alphabet. He started this, I think, when he was at Boeing. He was a lead engineer on the 777. He's a member of the National Academy of Engineering. He wanted GE to sell him didn't want to buy jet engines. He wanted to power by the hour. He wanted the most fuel efficient jet engines, and he wanted them constantly improve the jet engine, and he wanted to be future proof from obsolescence. And so we set that up in a similar way with our business. And the tenets of this model is a partnership with your customers. Your service has to get better over time. And to me, that's enabled by 100% smart hardware and investing in that, the ability to do that through over-the-air software upgrades and a network effect. And it's a win-win. Your customers see you have as much to gain as they do. And to me, I'd encourage you as you think about launching your businesses, because to me, there's a lot of tenets of what you're doing. But if you don't do it out of the gates, it's going to be harder and harder to do if you don't do it early. So I encourage you with that culture with your technology. So this is what we do. We do 3D printing. It was a breakthrough in material science for a window that uses light and oxygen to grow parts. This window allows light pass at 385 nanometers. It's a pattern of light, but because oxygen's coming through, the growing part doesn't bond to the surface and leaves a gap. And we can grow parts. And it allows us to go much faster, 25 to 100 to 1,000 times faster, depending on the resin and the object. But you notice that you should start changing the pattern of light. The part bonds to that metal platform that lowers into the reservoir, but it doesn't bond to the window, and there's a gap. And that gap allows the lifting part to suck resin in underneath it. And it deals with the mass transfer problem. It's not an adhesion issue per se. It's a mechanism for mass transfer underneath the part. And so we can now go much, much faster. Instead of a 2D printing over and over and over again, we can basically play movies and grow parts substantially faster. So this new world is happening with digital manufacturing. The physics are illustrated here. This is optical coherence tomography image actually showing you this gap and its mass transfer opportunity at the base of the part. Again, it's not an adhesion issue. A lot of people get this wrong in the literature. This is a mechanism for mass transfer by allowing a river of resin to flow in under the part. And we've modeled this extensively. And as we understand how the process gets better and better over time, again, I think of this as a software controlled chemical reaction to grow parts. And so as our digital twin matures and we understand new resins, new capabilities, the mechanics, we can upgrade the software and improve the printing process. And again, then there's a network effect associated with that. We invented new approaches for resins. Now that we're printing really fast, you want the part to come out to actually be a final part to move into manufacturing. And we approached new chemistries for doing that. I don't want to go through those details. Happy to talk more through that, but we have resins that are elastomers. We have rigid materials. We have materials with a master file at the FDA. We have biodegradable systems. We have water soluble systems. We're really deep in dental. There's lots of opportunities. It's the world's first FDA approved 3D printed denture. We've got tens of thousands of people now wearing dentures that are digitally printed. They're better. You go from 8 chairside visits to 2 chairside visits. A lot of advantages there. And this whole idea is we're going faster and we've really moved into manufacturing. And so we built the printers with 100% smart hardware. They're infinitely upgradable. Their design files remain on their printer, on a computer on their printer behind their firewall. It's all encrypted. Lots of protection with that. And we start to integrate these into factories. And so that platform where the parts are printed on, it looks like just a plain piece of steel, but it has a near field communication tag on it. And so as every part is transitioned from one part of the operation to the next, we tracking this all with software in a time-stamped way in the cloud. And then every part has got a unique barcode on it. And I think of every part as being alive because every part has a unique record in the cloud. And everything is streaming to that file. So we know which printer, we know which data file, we know which lot of resin, we know how many photons went to every part, and it's all being tracked. And so the cloud can bring you a level of knowledge. And again, I think of each part as being alive. We have its birth certificate, we have its grades in school, we have its death certificate, and we can even quantify recycling. And so you start stitching together factories when you do this, even the bigger printers. And now we've grown to, where there's lots of printers coming together, making products at commercial scale. And as you build, bigger build areas, you have to transition and grow your hardware. When you had a small area printer doing things like dental, and now you move to a printer that's got 5 times the build volume, right? You have to do things differently. Now you're bringing in resins with a meter mix and dispense instead of these little plastic containers. You can't afford to wash parts before you process them, too much mixed waste. Now we spin them solventless using a centrifuge. We collect that excess resin that goes back into the printer, and we do large scale curing. And so this is showing you that centrifuge. You'll see a pair of running shoes come off of that. Again, everything's being tracked. The NFC tags are everywhere. The parts have a QR code on them. Everything's being managed. You'll see the parts being split off the stage, all handled by robotics. And again, data is streaming to every part. And so this new world where all parts are alive, including their performance in the field, opening up new business models, and then including when they're going to be recycled, and now using data to help quantify your effectiveness in your programs. So this opportunity for traceability and modern software architecture, where you literally have every part being identified, and when I talk about new business models, the idea if there's a defect, you don't have to recall 100,000 cars anymore. Go look at the data. Maybe you have to recall only 1,200 because you have all the data, and maybe it was a bad lot of resin instead of every part. Again, that's where this data central world comes. I'm going to skip the video, but it really opens up a whole new world for manufacturing. And I think for us, what going digital also means is changing the way people design products. It used to be you design in your favorite CAD tools, And when you enter the real world, you go from bits to atoms or molecules. You go to a prototyping technology that's not your manufacturing technology. It's typically not your real end of material. And you do all that because you got to cut a tool for molding before you manufacture. In this new world of going digital, is you cut out those two middle steps. It's a disintermediation. And disintermediation, in whatever form it's in, is a classic Silicon Valley sort of playbook thing. Anytime you disintermediate, you get people out of the process or steps out of a process, you can scale more quickly. And that's what we do. And one area we're driving right now is very high resolution printing. We're printing microneedle patches for transdermal delivery of vaccines. We built printers down to 1.5 micron resolution pixels. And you can see these kinds of patches, and we just had a paper come out talking about this. But a lot of the target cells for vaccine are in the dermis. We have 100 to 1,000-fold more immune cells in our skin than we do in our muscle. We can get a 50-fold increase in vaccine and antibody response by locally delivering vaccines to the right spot in the body versus into the muscle. So, for us, additive manufacturing's got a lot of overarching advantages. It's an atom efficient process versus subtractive manufacturing. It opens up geometries that are unmakeable by traditional molding techniques. So topology optimization, architected materials. Making things with light is better than making things thermally. It's a key manufacturing technology for next generation tech fields like electrification of vehicles and space systems. The new business models of a circular economy where every part being alive, record in the cloud becomes really valuable. It allows supply chain adaptability and factory intensification, where you have a fleet of these printers that can make anything, and that allows you to run your factory flat out as your ebb and flow of product needs come, really opening up some neat opportunities. And you all see the backlog of ships in Long Beach and Singapore and other places. Shipping stuff from different parts of the world is not very economical. When a shipping container is 10 times the price today than it used to be just a year ago. And this idea of a warehouse in the cloud, really opens up some things. I love this quote from Thomas Friedman. On any given day, 2% of the world's GDP can be found in a UPS truck or package cars. And I think that percentage has grown given the backlog in the supply chain right now. And so this whole idea of local for local productions is really a tailwind for all of us. So anyway, as we think about additive manufacturing, all the different business models, all the promise, it's been held up by not having a digital fabrication technique that can scale or having the materials that really work and people not thinking about cradle to grave and back again. And I think if you really address these parameters, the makeable, the unmakeable isn't end use parts economically, thinking about circular economy, then additive manufacturing really takes off and the digital and the virtual merge together. So with that, let me end, and hopefully those were useful for what you guys are thinking about, and I'd be happy to answer any questions.
Thank you, Joe. We have time for one question. Oh, we have one in the chat, Joe. So do you think that this concept of traceability will become more of the norm in the 3D manufacturing sector?
Yeah. It's going to be the way to go. It opens up so many new business models.
So do you think they can just upgrade the safety and regulations?
Well, I mean, look, think about it. The opportunity for post-sale monitoring of products. Think about medical devices. Think about electrical connectors. 90% of the warranty issues in cars are caused by electrical failures. And 90% of those are caused by failed electrical connectors. And the idea that designs and materials play a really important role. When your car rolls into the service station, the technician's going to be able to scan the part. And if they had to replace the part, that data is going to go to the cloud, right? And it's really going to transform, I think, industry. in so many different ways. And so, yeah, I think that's all tied in. It'd be interesting to think about the tenets of what you're all doing in the front end laboratory automation all the way to end products. And how can you streamline, that'll be new waves of innovation if you can pull all that off.
Wonderful. Thank you very much for your stimulating, wonderful talk. I appreciate that.
Yeah, you bet. Good luck with
So
your
I would like to just welcome our next speaker. She is the last speaker of this session. So Professor Rebecca Doerge. She is a Glenn DeVoris Dean of the Mellon College of Science at CMU Carnegie Mellon University. She is a professor at the Department of the Statistics and Data Science, as well as the Biological Sciences. Her research is on statistical bioinformatics to understand the ultimate function of DNA and epigenomic association. Thank you, Rebecca. The floor is yours.
Can you see my slides in full screen?
Yes, absolutely.
Excellent. So hello, everyone. I'm Rebecca Doerge. I'm the Glenn DeVries Dean of the Mellon College of Science. I want to say up front that by training, I'm a statistician who went from math to human genetics to statistics to agricultural genomics and made a career out of chasing technologies and figuring out how to analyze the data. So today I want to tell you about a journey that we're on at Carnegie Mellon to build the first academic cloud lab. We have a mission to automate and democratize science, and I want to tell you how it's going. Let's see here. There we go. So I don't need to tell this crowd that we are at a change point in science. The future of science today is being driven by massive amounts of data, AI technologies, very much like my training, interdisciplinary work and education and boundaries are being challenged much more than they were 20, 30 years ago. And much of chemistry research and life science research is currently limited by the speed and the rate of data acquisition that we have. So let's talk about that. So at Carnegie Mellon, we've partnered with Emerald Cloud Lab, which is located in South San Francisco. It's founded by DJ Kleinbaum and Brian Frezza, both Carnegie Mellon alumni, College of Science. It is a remote controlled laboratory that has automated instruments. There are technicians in the facility, but no scientists that are conducting research. Everything is traceable, so it very much ties into Joe's talk. We can do both on-site synthesis, or you can send samples to the lab. This is based upon the Emerald Cloud Lab facility. It will be the first academic cloud lab in the world. And obviously, Emerald Cloud Lab is a for-profit. And when we think about a facility like this in a university setting, it's really transformational. And so I invite you to think about how this shapes the future and democratizes science and changes how we educate students going forward. So, 3-4 years ago, my question was, do we need an academic cloud lab? And I asked lots of people, and really, can we afford one? How do we do it? It's a completely different business model, like Joe was saying, than a for-profit facility. So research productivity, can you imagine having every instrument available in chemistry and biology under one roof, tied together by automation, software, and robots? The only limitation to your discovery is actually your own human ingenuity. So research productivity, I get really excited about that. Reproducibility, I warned you up front that I'm a statistician. So I imagine a day that we submit our work to a journal, Science, Nature, whatever, and we submit our manuscript. Of course, we have to submit our data, but we also submit a parameter file for science that's been designed and performed on a cloud lab, so that the next scientist or someone who challenges the reproducibility, they have your code. They can rerun it, get the same results, or they can take your code, your new sort of digital protocol, and they can tweak it a little bit and move your science forward. This is totally increases research productivity if you think about it that way. I've heard mention already of open science. This very much is a collaboration with CMU libraries. Our librarian, actually, our Dean of Libraries is actually a computer scientist. So he is very interested in open collaboration, knowledge sharing, and this fits right in. Educating the next generation of scientists, I think that that probably is the thing that motivates me most. At Carnegie Mellon, we're well known for engineering and computer science and educating the next generation of engineers and computer scientists, and science has to keep up. So we are very interested in working across the university to educate the next generation of scientists. This is a university facility that is envisioned through the College of Science. Democratizing science is really fun to think about. We have high schools and under-resourced universities that we're partnering with. I personally am first generation. I grew up in an extremely under-resourced community and have a completely under-resourced education. If I, as a high school student, had access to a cloud lab, I think it would have been transformational for sure. And then we are Carnegie Mellon. And so my anticipation for this cloud lab in academics is that we will move forward very much, again, like what Joe said, we will grow with new discoveries in instrumentation and robotics. We have a very active learning group where you are using AI and machine learning to move through your experiment, learning as you go. And ultimately in chemistry, you can, instead of doing, for example, every possible combination of things, in active learning, you can move through the experiments learning, and maybe you only have to do 10% of the actual experiments to get 95% of the information. So it's just really fun to think about. So, so while I was questioning and talking to the president of the board of trustees and everyone, everybody would smile and sort of say, "That's nice, Rebecca." And I couldn't really get the attention of the magnitude of this change point in science and what this is going to do to transform science. So I said, look, I need a really smart chemistry student. Meet Dima. Dima works on synthetic DNA, and traditionally in Dima's life as a PhD student at Carnegie Mellon, he could synthesize 3 compounds in a week because he knew what he was doing, and that was considered pretty good. We sent him to Emerald in South San Francisco for a month. We embedded him. He was not a programmer, and so my challenge to him was, can we teach you in 1 month enough for you to do research? And he essentially was able to, he told me when he came back, it took 20 minutes to write the code for his experiment that allowed him to do hundreds of compounds in a week. So we just took a very smart scientist, which it's a great story on its own. And he was my proof of concept. So good news is Dima graduated and he now works at Emerald Cloud Lab. More recently, proof of concept for automation and AI and polymer synthesis was done by Olis here, and he's in the chemistry department at Carnegie Mellon, and he works with his colleagues at Chapel Hill to find ideal candidates for MRI imaging agents, which anybody who does this knows that it would take, you wouldn't even imagine testing 50,000 monomer compositions. You just wouldn't imagine it. Time-wise, money-wise, it would be likely impossible. So using artificial intelligence and active learning that I actually just mentioned, Olis and his colleagues, they didn't have to go through 50,000 monomers. They actually, in less than a week's time, were able to test 400 polymers. So this is 2021 proof of concept. So we're very motivated by this. Our faculty are excited. Our students are excited. And people, they just can't wrap their head around our facility in Pittsburgh will have about 250 instruments, chemistry, biology, life science instruments. We are working with the major instrument companies to do this. And so when I give this talk to scientists, we typically just put up things that people, can you do this? Can you do that? And this is by no means the whole list, but this is just an example. The Carnegie Mellon Cloud Lab will have 11 more instruments, different instruments than Emerald Cloud Lab, and will be slightly bigger square foot wise. So I kind of enjoy saying that. This is an example, a cartoon of a cloud lab, and imagine each of these little gray boxes as being an instrument. And the cool thing is that you can tie these little gray boxes together any way you want. So on the right here, you see 3 different, completely different workflows, all taking place in the same cloud lab. So during construction, and pretty much as soon as we realized that we wanted to see if we could do science using a cloud lab, we were given access by the generosity of Emerald Cloud Lab. We were given access to their facility in South San Francisco. So we had scientists and students sitting in Pittsburgh coding their experiments, submitting their experiments, and the work was being done in South San Francisco. The good news here that I'll mention is that we had access to the cloud lab during COVID. So just to give you an example of some of the research that's going on, and I show this slide to show the breadth of the research that's going on. We are currently training faculty and students and postdocs and research faculty to use the cloud lab. These 3 scientists, one is in chemical engineering. She works on synthetic DNA and PNAs. Lynn Walker is a physicist who works in rheology, and that's actually deformations of the flow of matter, which is really, really cool. Anyway, I won't drag you through it. And then Wai Ying, she works on subcellular processes related to cancer cell growth. And the cool thing here is that she works with high schools in Pittsburgh. And so she's connecting the cloud lab to high schools. And then more on the side of education, and I really enjoyed your readouts from your working groups yesterday. Marcel Boucher and Suba Das have incorporated the cloud lab into undergrad classes. So during COVID, when we had to shut down our wet labs, we seized that moment to train more faculty, but we also seized that moment to learn how to teach a class using a cloud lab. I was very hesitant about undergrads having the computing capability to do this, the knowledge on coding, and in one of the readouts you mentioned this. Suba Das, he definitely went for it. He's a faculty member in chemistry, and the first class started with 12 undergrads, all remote, of course. It was during COVID, and 11 of them finished. The one person that didn't finish, it was because she didn't have her internet connection was weak because she was someplace else in the world. Suba's students are publishing their work, which is amazing. And I just want to say that students have a better first experience with chemistry. They have a better first experience with wet labs because there's no human, it's not an issue anymore of people who have good hands and people who don't have good hands. It's a better experience off the bench. So maybe this is, an opportunity to help STEM grow a little bit. And then Chris Langmead, he works in optimization of workflows in a cloud lab, which is a whole blossoming area. And I just want to say that we know that by putting a cloud lab in an academic facility, that we are probably creating new disciplines that we don't know about yet. We're opening a can of worms. But right now, our first goal is to get this thing built. That is going on right now. It will not be on campus because I do not want faculty in it, but it will be in Pittsburgh, 2 miles from campus. And I'll show you this slide because later on, I have a 2-minute video. I don't want to waste time showing it, but if anybody wants to see it at the end, I'm very happy to show you sort of testimonials from the students. It's a professional video, it just has a student that talks about the experience. So the practical advantages here are obviously shared cost and instrumentation. The days of inviting an assistant professor to join your university and $2 million startup packages. Now this is very much like shared computing. You buy threads. So in shared computing, you buy nodes, and on the cloud lab, you buy threads. And so I can imagine probably next hiring cycle, we will include threads on the cloud lab. for our incoming faculty. Do I think that all of science is automatable? No. Do I think that more than half of the repetitious work that people stand at a bench doing is automatable? Yes, and that's really the goal here, and to grow this forward. So it's very exciting to think about how it will go. You know, back to faculty, they can start research on the first day. They're not limited by, you know, renovations and waiting for things and spending a year starting up their lab. And then again, the collaborative possibilities and the ability to really expand disciplines, engineering, robot, computer science, is very, very exciting, not just for Carnegie Mellon, but for the whole world. So this is a transformational time in science. Cloud labs are part of that. It deals with reproducibility, increased productivity, open science, and I've mentioned active learning. So it really is a very transformational time when we think about this. And with respect to society, it is able to address challenges. Let's face it, if we had 10 of these cloud labs around the world, we could have addressed COVID even faster than we already addressed it, which was really super fast. Flexibility, this is a very modular laboratory. So if you're a pharmaceutical company and you only need these 30 instruments, then those are your 30 instruments that make up a cloud lab. The one at Carnegie Mellon, we had a working group and I said, give me your wish list. And a wish list turned into 250 instruments. But so it's flexible. And I can imagine a day that if we see this thing runs 24/7, 365, I can imagine if there's a wait line and it's prioritized just like computing. If there's a wait that time to get something done on a certain instrument, you just buy another instrument, and plug it in. And then you have more capability, and you can back out capability as well if things aren't being used. And then the democratization of science. I really think that this is exciting to think about, to put in the hands of really smart people instruments that in a career they could never accumulate. We all have colleagues that are at under-researched universities that can't get funding, but we all know they're brilliant, and typically they just love to teach, and they just love where they're living, and they just suck it up. Imagine giving these really, really talented, bright people access to a cloud lab, so it doesn't matter where you are in the world or what under-resourced university or high school or whatever you're at, you would have access to this. So this is happening in Pittsburgh. If you know Pittsburgh, it's in a place called Bakery Square. Google's Pittsburgh headquarters is there. We're maybe 2 doors down. So we have the location. We have, this is a $40 million project, full freight, if we don't get an academic discount, let's say. So that's full freight. Our financial planning, we have a business model. The university approved it, which I love that one line. It just, we have a major donor. We have hired the architect and engineering firm. We are renovating the space. About 3 weeks ago, I walked through the space, super exciting. We're in the process of finalizing equipment negotiations with the instrument companies. And then by this time next year, we will be fully operational. So learning how to run a cloud lab in an academic setting is our next challenge. So I'll end there and take questions.
Thank you very much, Rebecca. So we have one question in the chat, if you don't mind. Oh, so Jared, do you want to go first? Okay, I go first. So we have 2 questions. So the question number 1 is, what is the scale of the materials produced? Milligram, gram, kilogram?
All of the above.
All of the above.
Yeah, and I encourage you all to, if you go to Emerald Cloud Lab, that's their website. There's a 2-minute video, maybe 2.5 minutes, that describes very succinctly. And actually, one of their examples is, we can handle this much to this much to this much. So please watch that. And I'm not a chemist by any means, but I'll answer the questions the best I can. But I do know that one.
Wonderful. Question number 2 from the chat. So how many researchers can work in this cloud lab at a time?
Yeah, so good question. Obviously each instrument can only work on one experiment at a time, or if you have multiplexing on an instrument, as a statistician, I could do all possible combinations for you, and that's the number of faculty that could work on it. I don't know, that's the honest answer. No one's ever asked me that question. Let's just say a lot. Another question that I get asked a lot is how many people does it take to run this? Because I say very openly to everyone, I do not want faculty in this. People are not, when you take tours, you're in a white coat with your hands in your pocket sort of thing. We think, so Emerald Cloud Lab, we have access to their proprietary software, which is really the secret sauce here. And Emerald Cloud Lab has agreed to run the facility for us for probably the first 3 years. The business model, we know that we will, Joe kind of mentioned this too, it's the swoopiness of starting a business. We know that we will run in deficit probably to the level of $5-6 million and then start turning a profit in year 4. So we're good to go there. And it's fun and exciting. So I have an answer for you. Ed Dunley, who is our director of industrial relations in the College of Science, just answered the question for me. We can have up to 50 to 70 threads at a time, depending on the number of operators. An operator is a person on the floor. So thank you, Ed, for saving me.
Very impressive.
Let's see, hold on. How do you plan for equipment downtime?
Yes.
Yeah, so, well, clearly, if you need to service an instrument, and I want to talk about this, if you need to service an instrument, then clearly that instrument's blocked if you only have one, right? If you have multiple ones, then you're good to go. And you do the service and then you bring it back up. But the cool thing about capturing everything about this environment is that, so statistician in me, temperature, time, right? But I also know which instruments and I know the life cycle of that instrument. So I can measure deviations from norm and watch every single aspect of the cloud lab in real time. And you guys, know this, that many instrument companies, they also are hardwired in that they can tell when their instrument needs to be serviced or something's wrong. So for statisticians in the crowd, this is going to be fun. So let's see.
Jared,
and I want to shout out to Mike Lewinsky, who is a grown up now, but he was a PhD student in chemistry at Purdue when I was there, and he took a genetics class from me. And I'm just so happy to see him on this side of the world, like he survived.
Jared, do you want to go next?
Yeah, thank you. A fantastic talk, Rebecca. And we in PNG, by the way, have started to work with ECL and we are fascinated. Yes. One of the things is we can see, like you, that it works very well when methods are standardized and yes. well qualified. Do you have any experience or any plan to, with your CMU Cloud Lab, to deal with methods that needs to be, how to say, created and developed with the innovation, or are you focusing on standardized methods?
Yeah, I understand the question. Right now, we're just focusing on standardized work. This Cloud Lab is part of a greater science future initiative at Carnegie Mellon that will have a science building, right? A new home for science. And that new home for science will have 20% less wet labs because of the Cloud Lab. Okay. And we will have space dedicated to exactly what you just said, the figure it out space, right? And then if you really want to have fun, and I hope Joe's still on the line, but if you really want to have fun, think about the entrepreneur side of this, the startup side of this. If you have an idea and you have a space and a place in a new science building that you can generate your new idea, test it out, right? Then you don't need to find wet lab space, which is a high commodity in Pittsburgh. You don't need to find computing. So someone told me rate to failure is increased, right? So you know if you're going to fail, you're going to succeed much, much quicker if you have access to that space that you just mentioned, Gerald, Gerard. And then you can, if the startup world has access to a cloud lab, then you can just spin it off directly to the cloud lab. So it's really exciting. And the same thing goes for instrumentation as well, right? So yeah.
No,
And again, I always have to say that, like, we're opening a can of worms, and these questions are the best because we're really not sure which road we're going down.
Well, it's reassuring, if I may, to see that you are going through 3 years of valley of investments to see the light later. This is fascinating for all of us. And I think one of the ideas, to make sure I get it right among many, is you are going to save space, time on, let's say, standard routine stuff in order to reinvest it. That's what you say, into more innovation, whether it's startups or whether this is phenomenal. Very good.
Yeah, I mean, that's my vision for this. Okay, I know that the first couple of years we're just going to learn how to run a cloud lab and how to use it in education. But my idea here is that this will be fully supported by the whole university. Engineering, you know, if there are statisticians who want to learn how to do wet lab science, traditional, you know, standard stuff, they don't need to learn bench skills anymore. Right. So this really does enhance interdisciplinary teams in a very unique way. And by the way, I do not have good hands at the bench. Anyone at Cold Spring Harbor 20 years ago could tell you that. So you know, I just keep thinking what would have happened if I had something like this when I was in grad school.
We have more questions, but we are out of time. Please put it in the chat that Rebecca would be able to answer those. Thank you so much, Rebecca, for the
Thank you, everybody,
talk.
for inviting me. I had a good time. Thank you very much.
Thank
Linda,
you, all
thank
the
you.
speakers. So I would like to welcome Marty and Nikki back to the Zoom for their closing remark. Thank you very much, everybody. Marty and Nikki, Zoom is yours.
Yeah, so thank you so much to all of you, to the participants, to the speakers, to the organizing committee, everyone who participated in the breakout rooms and in the chat and the discussions. This has been just a fantastic day and a half. Marty, what do you think you've learned from all this day and a half?
Awesome. Thank you so much. My head is still spinning. I mean, this has just been absolutely phenomenal. I think one of the most important messages we heard constantly from our 100 colleagues all teaming up together to have this amazing conference is let's make sure we do something, right? So there's just so much momentum as emphasized so powerfully in the talks that we just saw. This is a moment of change. This is a disruptive time in our field. And it's going to revolutionize everything about who we are and what we can do. And I think the very strong message that's coming out is that we need to capture this moment and turn it into action. And I think one of the most exciting things for me is how many people commented their interest and passion and excitement about teaming up to make a difference and to leverage this moment to achieve something extraordinarily special. I don't know, what was your biggest takeaway, Nikki?
Yeah, so I totally agree. So some logistics, you know, there's a recording of this. Many of you have noticed that, and that's going to be posted on the Chemical Sciences Roundtable website within the next 2 weeks. And an email announcement will go out once the recordings are available. And there's also a proceedings and brief that summarizes the events from the workshop. So that's going to be published by the National Academies by early spring of next year. But frankly, I don't want to wait till early spring of next year to get moving. You know, there's this textbook project. There's a whole consortium that we can get together. There's the lab in a box. There's so many different ways so people can start participating. And the first thing you can do is go out and tell your colleagues about what you learned at all your different universities and companies and wherever you're at now. Just, you know, have lunch with them next or coffee and tell them what's going on so that we can incorporate and include more people in this whole endeavor.
Absolutely. I mean, that was the other, I think, incredibly exciting theme that came through. You know, as a field, we've had barriers that have limited access to so many amazing, talented people, right? Rushing into our field and revolutionizing the way we think and the way we solve problems. This is our moment, right? We can shatter those barriers. Automation is incredibly powerful, both from a technical perspective, but I think the message that came through loud and clear, this is much bigger than automating an experiment. This is about revolutionizing access to the molecular innovation process. And if we can finally shatter those barriers and invite everyone into that molecular innovation sandbox. I mean, this is going to be absolutely phenomenal. You know, it always amazes me. We've been making tools on the macroscopic scale for like 2 million years, right? Arguably, this was that pivot point which made us human. And society has, of course, been revolutionized by so many of those tools in so many positive ways. We've only been making molecular tools for like 200 years, at least on purpose. So we've like at the infancy of what's possible in terms of molecular tools. And there are so many challenges facing society for which there are molecular solutions out there that we just haven't discovered yet. And so I think as Benji highlighted and as Rebecca just so incredibly powerfully emphasized, what if we had 1 billion amazing imaginations have access to help solve those problems? It's going to just absolutely transform everything about how we find those solutions. So it's just an incredibly exciting time. And thank you so much to everyone for your remarkable, passionate engagement over the last day and a half, that I think this is going to be a real turning point in how we move forward.
I totally agree. And the thing that struck me, right, we started our coffee conversation yesterday morning wondering if this is going to take our jobs, and talk after talk after talk, including this morning, it keeps coming back to people. Getting the people together was a big challenge for Joe DeSimone. Rebecca's like, now how are we going to manage this cloud lab to make it most effective? That's the big challenge coming about. So it's really fascinating how we've been talking about automation this entire day and a half, but a lot of the problems are coming down to people skills. How do we organize people? How do we get people together? How do we make effective use of this technology and these machines for specific goals? I love Joe DeSimone's value statements, right? The values that we have, how do we translate and act on those values in the course of developing this next wave of science and technology?
Absolutely. And same, I think, you know, when Alon talks about bringing AI together with this automation and creating these consortia that we were dreaming about, and he's already got great momentum going on. For example, in Canada, we learned that this is really an international opportunity, right? So we can think about partnering in so many amazing ways to build on that momentum and leverage those tools and learn from each other, so that the ultimate whole is going to be so much greater than the sum of the parts. And I think, you know, the potential moving forward, if we team up and make these kind of very futuristic envisioned objectives into reality, there's just really nothing that can't be accomplished once we get to that point.
I totally agree. But of course, every big dream starts out with little baby steps. And Rebecca had a nice, and Joe also, and Alon had a nice way of like, these are not just things they did yesterday. These were plans they had, visions that they collected people and resources together, and slowly but surely built up something that's starting to bear fruit. And so what sort of baby steps are you going to take, Marty, when you get home?
Awesome. I'm already running around my office. Actually, I had to sit back down just to be embarrassing if I was running in circles as I gave this final statement. So I honestly, it's so exciting. So, you know, as you know, here at the University of Illinois, we've got this Molecule Maker Lab Institute that we've been very fortunate to get funded by the NSF. It just beautifully complements so many of the things that are being talked about today. And we are really looking forward to partnering with lots of different groups who are interested in the same thing. You know, Nikki, you and I have been talking about this a lot. So on that macro scale, I think that's a mechanism that I'm really excited about and looking forward to building those bridges. And I'm also really excited about all three of the projects you just mentioned. So for people who are interested, there's 3 action items moving forward, right? The automated synthesis experience in a box. We've got the living, breathing textbook that you've brought forward. And then this idea of a consortium that can bring us all together. I'm excited about all 3 of them. So I'm looking forward to contributing.
Yeah, me too. And also seeing how we can bring in more people from outside North America as exciting opportunities also. How do we bring in the rest of the world? Because there's so many problems that to be solved that are also very place specific. And how do we make sure that, like you said, that ideas get shared freely in a way that we can build up the science and technology. So yeah, Anne already have our time scheduled for starting work on the textbook. We'd love to get some sort of draft so that people thinking about their classes next fall can already have something at least to look at and as a starting point. And we look forward to really participating in all the other portions of this too, the lab in a box and the consortium and how we get people together and seeing how we have an umbrella organization that might be able to help us put all this together.
Awesome. Yeah, so on the same, we're not kidding around about that lab in a box. So we're really excited to actually turn that into a real thing. As mentioned, Rachel Switsky kind of brilliantly driving this forward. And I know she's looking forward. Anyone who's interested in joining up, please reach out directly. We'll have another follow-up workshop just to further plan what could go into that. box, and then how do we distribute them to the world? And to get back to Jake's suggestion, how do we team up and do kind of collaborative experiments globally, generate collections of data that everyone can share, learn how to work in teams, learn how to leverage that synergy that just kind of naturally falls in place. And again, automation ends up being a vehicle for teamwork, for engaging each other, for finding new ways to solve problems. So I think all of those are super exciting. I know Shane and Bob are very excited about the consortium and finding ways to move all of that forward as well. So we're not kidding around. The goal is to turn all this into action items, and anyone who wants to join up and partner and make that happen, we're really excited to have those teams come together.
Yeah, so maybe we need to get another coffee chat together here pretty soon.
Awesome. And I switched now. You inspired me. So I went to my local coffee shop this time. So, all right. Thanks so much for the nudge. Awesome. Okay, well, it leaves us just to thank everyone so much again for taking such a really precious amount of time the last day and a half. Hopefully everyone feels like I do, and Nikki, I know that was just tremendously worth it. So much exciting momentum coming out of this. The wind is at our back, so let's run, and make this happen. All right, thank you so much, everyone.
Bye-bye.
Bye.